Welcome to this explainer. When most of us look at a bullet train, we kind of just see a really fast version of a normal train, right? But from an engineering standpoint, that literally couldn't be further from the truth. Pushing multi-ton metal tubes across the landscape at hundreds of kilometers per hour isn't just an upgrade in speed, it is an entirely different physics paradigm. The forces at play become so extreme that they require radical, completely reimagined civil engineering and infrastructure. Today, we're going to unpack the invisible forces keeping these trains on the tracks and examine the incredible structural countermeasures designed to defeat them. So here's our roadmap for today's explainer. We'll be covering the high-speed physics paradigm, managing aerodynamic bursts, conquering tunnel shockwaves, bridge resonance and stability, and finally, the passenger comfort equation.
All right, let's jump right into part one, the high-speed physics paradigm.
Okay, so to really appreciate high-speed rail, we have to understand how extreme velocities completely break all the standard railway design rules. At these crazy speeds, microscopic attention to infrastructure design isn't just a luxury, it's absolutely crucial for basic stability. In traditional railway engineering, structural design is largely based on static load models. You just take the weight of the train, multiply it by a basic dynamic factor, and you build your track. Simple. But for high-speed rail, that classical static assumption is completely inadequate because the train is moving so incredibly fast. The structures below it don't just hold weight. They have to react to violent, rapidly changing forces over fractions of a second. This requires what we call transient dynamic analysis. Engineers literally have to simulate actual train loads moving at high speeds to see exactly how the tracks and structures are going to vibrate, bend, and recover in real time. Moving on to Section 2, managing aerodynamic pressure bursts. Let's take our journey out onto the open track to see these extreme forces in action. Picture this. You're sitting in a train, cruising along at 350 kilometers per hour. Suddenly, a train going the exact same speed blows past you in the opposite direction. From a physics perspective, those two massive objects are tearing past each other with a combined speed difference of 700 kilometers per hour. 700. That is almost the cruising speed of a commercial airliner, and it's happening just meters away, right on the ground. And that 700 kilometer per hour passing speed, it creates a massive aerodynamic threat. As the trains meet, there's an immediate, violent burst of air pressure, which is instantly followed by a severe pressure drop slipping right between the passing carriages. Now, while this isn't quite enough to actually blow the trains off the tracks, thankfully, this violent push and pull severely stresses the sides of the cars. Without proper infrastructure planning, this repeated stress can cause the window glass to undergo severe fatigue and literally break mid-journey. No way we want that. So how do civil engineers actually solve an invisible air pressure problem? Well, they physically widen the railway. Looking at the formation width and spacing requirements for these transverse sections, you'll see that to manage these aerodynamic pressure bursts safely, high-speed tracks must be spaced significantly further apart than standard railways. It's a really costly requirement. We're talking wider land acquisition and much broader embankments, but it is absolutely critical. You have to dissipate that violent airburst before it hits the passenger windows. Okay, Section 3, conquering tunnel shockwaves. Now, if open tracks present aerodynamic challenges, enclosed spaces kind of turn them into nightmares. Just think about this for a second. What actually happens to the air when a massive, solid object plunges into a narrow, enclosed tube at 350 kilometers per hour? Well, the air has absolutely nowhere to go. It can't easily slip around the sides. Instead, it gets violently compressed. And this creates a pretty terrifying phenomenon known as micro-pressure waves. When the high-speed train enters the tunnel, it generates a pulsed compression wave that shoots through the tunnel at the speed of sound. And here's the crazy part. The pressure gradient of this wave isn't just proportional to the train's speed, it's actually related to the cubic speed of the train. That means even a tiny increase in speed creates a massive exponential leap in pressure. When this wave finally reaches the exit portal, it radiates out as a literal explosive sound, often called a tunnel boom, and it causes heavy, really alarming vibrations on the train's doors. This is exactly where we see structural and vehicular solutions having to work perfectly in tandem. To mitigate these explosive shockwaves, engineers have to build massively increased cross-sectional areas for the tunnels. They often even opt for independent, single-track tunnels just to avoid the compounding aerodynamic drag of two trains passing underground. They also construct these specially designed tunnel hoods at the entrances. These act like giant buffers and are actually up to 1.5 times the diameter of the tunnel itself. Plus, they install vertical pressure release shafts. And on the vehicle side, this is exactly why Japan developed trains like the Fast Tech 360 with ultra-long 16-meter streamlined noses. They're shaped using complex 3D fluid dynamic analysis just to slice into that air smoothly.
But even with all those brilliant solutions, incredibly strict safety limits still remain. Infrastructure specifications state that tunnels must be designed so that the maximum pressure variation along a standard high-speed train doesn't exceed 10 kilopascals at maximum speed. Now, why exactly 10 kilopascals? Because that is the absolute biological limit required to protect the eardrums of the passengers, just in case the train's own internal sealing system happens to fail while it's inside the tunnel.
That brings us to Section 4, Bridge Resonance and Stability. Bringing our journey out of the dark tunnels and up onto a soaring long-span bridge, the physics challenge completely shifts. When you look at the angular rotations and dynamic deflections of a bridge deck under load, you realize high-speed trains aren't just heavy. Their weight is distributed across perfectly spaced bogies or wheelsets. When a train crosses a bridge at hundreds of kilometers per hour, the regular, repeated pounding of these bogies hitting the spans at exactly the right speed can actually trigger dangerous resonance. It's kind of like pushing someone on a swing at the exact perfect moment. This resonance causes massive amplifications in the bridge deck's vertical deflections.
And if that bridge resonance isn't perfectly managed by the transient dynamic analysis we talked about earlier, something truly terrifying happens. If the bridge deck's upward and downward acceleration becomes too extreme, the crushed stones beneath the track, which we call the ballast, actually lose their cohesion. Because of the intense high-frequency vibration, those solid rocks literally begin to behave like a liquid. And as you can probably guess, your track turning into soup is definitely not ideal when a train is rocketing over at a top speed. It instantly destroys the stability of the long welded rails bolted above it, leading to a complete catastrophic loss of track geometry.
Finally, let's look at Section 5, the passenger comfort equation. So we've talked about pressure bursts, shock waves, and, liquefying track ballast. But all of these extreme structural limits ultimately connect back to the person sitting in seat 14B. To ensure a high-speed train doesn't violently sway and cause passenger discomfort, the infrastructure is subjected to incredibly strict serviceability criteria, specifically for how much a bridge deck is allowed to twist under load. For slower speeds under 120 kilometers per hour, a maximum twist of 4.5 millimeters over a 3-meter gauge is allowed. But the second you push that speed higher, the limit tightens strictly to a microscopic 3 millimeters. Just try to imagine engineering a massive concrete bridge span and demanding it twist no more than the thickness of a few sheets of cardboard while a multi-ton train slams into it. So, the crucial point here is that all of this massive civil engineering ultimately serves a very human biological limit. The ultimate goal is to keep the vertical acceleration experienced by the passenger as low as possible. To achieve a ride that's classified as very good, meaning it's perfectly smooth and you definitely won't feel nauseated, engineers must ensure the vertical acceleration of the train carriage never, ever exceeds 1.0 meters per second squared. That requires the track, the bridges, the tunnels, and the train itself to operate in absolute perfect physical harmony. From widening tracks to stop aerodynamic glass-shattering pressure bursts, to tunneling massive release shafts to prevent sonic booms, to managing bridge resonance so the very ground doesn't liquefy beneath the wheels, high-speed rail is an absolute marvel of extreme civil engineering. So, the next time you're gliding effortlessly across the countryside at 350 kilometers per hour, comfortably sipping a coffee, will you ever look out that train window the same way again, knowing the invisible physics and massive infrastructural forces working furiously right beneath your feet to keep you safe?